Hello everyone. So in today's video I'm going to go over this paper from ICLR 2018 titled Synthetic and Natural Noise Both Break Neural Machine Translation by Jonathan Belinkov and Jonathan Bisk from the Computer Science and Artificial Intelligence Laboratory at MIT and Paul G. Allen School of Computer Science and Engineering, University of Washington. Right. So this paper came to my eyes because I was working on some methods for data augmentation in NLP, and one of the libraries mentioned this paper for one of the functions because what they were essentially doing was adding random characters or replacing random characters in sentences to make the dataset more robust and make the machine learning models trained on those datasets more robust to real world typos and stuff. So that's why this paper was pretty interesting, and I'll be covering it. Alright, so the abstract character-based neural machine translation (NMT) models alleviate out-of-vocabulary issues, learn morphology, and move us closer to completely end-to-end translation systems. Unfortunately, they are also very brittle and easily falter when presented with noisy data. In this paper, we confront NMT models with synthetic and natural sources of noise. We find that state-of-the-art models fail to translate even moderately noisy texts that humans have no trouble comprehending. We explore two approaches to increase model robustness: structure-invariant word representations and robust training on noisy texts. We find that a model based on a character convolutional neural network is able to simultaneously learn representations robust to multiple kinds of noises. So basically, they've outlined the issue which current the models at that time had with noisy inputs, and they've also presented two approaches which gave them success in combating this issue. Alright, so for the introduction, humans have surprisingly robust language processing systems. They can easily overcome typos, misspellings, and the complete omission of letters when reading. A particularly extreme and comical exploitation of our robustness came years ago in the form of a popular meme. So I'll just read it normally. According to a research at Cambridge University, it doesn't matter in what order the letters in a word are. The only important thing is that the first and last letter be at the right place. Okay, a person's ability to read this text comes as no surprise to the psychology literature. Savary and Perrott found that this robustness extends to audio as well. They experimented with playing parts of audio transcripts backward and found that it did not affect comprehension. Rayner et al. 2006 found that in noisier settings, reading comprehension is only slowed by 11%. McCusker et al. Found that the common case of swapping letters could often go unnoticed by the reader. The exact mechanisms and limitations of our understanding system are unknown. There is some evidence that we rely on word shape, that we can switch between whole word recognition and piecing together word from letters. And there appears to be no evidence that the first and last letter positions are required to stay constant for comprehension, which was claimed in this meme. Alright, so in stark contrast, neural machine translation systems, despite their pervasive use, are immensely brittle. For instance, Google Translate produces the following unintelligible translation for a German translation of the above meme. Okay, so they've just mentioned on what they did this, because now if you do this, the algorithm might have changed, the backend model might have changed. While typos and noise are not new to NLP, our systems are rarely trained to explicitly address them, as we instead hope that the relevant noise will occur in the training data. Despite these weaknesses, the move to character-based NMT is important. It helps us tackle the long-tail distribution of out-of-vocabulary words in natural language, as well as reduce computational load of dealing with large word embedding matrices. NMT models based on characters and other subword units are able to extract stem and morphological information to generalize to unseen words and conjugations. So, to explain this point, how does it help to reduce the computation loading? Essentially, if you're using only word-based embeddings, there are more number of words than there are characters, right? Because words are essentially formed from combinations of characters. So the larger your vocabulary, the more words you want to incorporate, the larger your word embedding matrices become. So that's why if you use characters, that computational load reduces. They perform very well in practice on a range of languages. In many cases, these models actually discover an impressive amount of morphological information about a language. Unfortunately, training and testing on clean data makes model brittle and arguably unfit for broad deployment. So figure 1 shows the performance of two state-of-the-art NMT systems degrading when translating German to English as a function of the percent of German words modified. We show three types of noises: random permutation, swapping a pair of adjacent letters, and natural human errors. We discuss these types of noises and others in depth in section 4.2. The important thing to note is that even small amounts of noise lead to substantial drop in performance. So you can see even when there's 20% noise, your score has fallen from roughly around 35 to 15. And these are the two models, Nemetis and car to car. To address these trends and investigate the effect of noise on NMT, we explore two simple strategies for increasing model robustness: user structure invariant representations and robust training on noisy data, a form of adversarial training. We find that a character CNN representation trained on an ensemble of noise types is robust to all kind of noise. We shed some light on the model ability to learn robustness to multiple types of noise and point to remaining difficulties in handling natural noise. Our goal is twofold. First, initiate a conversation on robust training and modeling in NMT, and second, promote the creation of better and more linguistically accurate artificial noise to be applied to new languages and tasks. Alright. So I guess this part was pretty clear. They've just outlined the problem, why it's there, empirical evidence for its presence, and what they're going to be doing. So for adversarial examples, the growing literature on adversarial examples has demonstrated how dangerous it can be to use brittle ML systems so pervasively in the real world. Small changes to the input can lead to dramatic failures of deep learning models. In the machine vision field, changes to the input image that are indistinguishable by humans can lead to misclassification. So you must have seen those examples where a single pixel was changed and the model converted a cat to a dog or things of that sort. This leads to potential for malicious attacks using adversarial examples. An important distinction is often drawn between white box attacks, where adversarial examples are generated with access to the model parameters, and black box attacks, where examples are generated without such access. While more common in the vision domain, recent work has started exploring adversarial examples for NLP. A few white box attacks have employed the fast gradient sign method or other techniques to find important text edit operations. Others have considered black box adversarial examples for text classification or NLP evaluation. Heigold et al. Evaluated character-based models on several types of noise in morphological tagging and machine translation and observed similar trends to our findings. Finally, Sakaguchi et al. 2017 designed a character-level recurrent neural network that can better handle the particular kind of noise present in the meme mentioned above by modeling spelling correction. Here, we devise simple methods for generating adversarial examples for neural machine translation. We do not assume any access to the NMT model gradients, instead relying on synthetic and naturally occurring language errors to generate noise. So basically they've defined what adversarial examples are. There are two types of adversarial attacks: white box attacks where you have access to the model parameters, and black box attacks where they are unknown. And then again, they've mentioned some works which have tried to do this, for instance, and have gotten similar results. For instance, the work by Heigold et al. And they've also mentioned this work by Sakaguchi, where they designed a character level RNN, which was able to handle the issues presented by examples such as this meme, and it handled it using some sort of spelling correction modeling, which seems pretty interesting to check out later. Alright. The other side of the coin is to improve models' robustness to adversarial examples. Adversarial training including adversarial examples in the training data can improve a model's ability to cope with examples at test time. This kind of defense is sensitive to the type of adversarial examples seen in training, but can be made more robust by ensemble adversarial training on examples transferred from multiple pre-trained models. We explore training We explore ensemble training by combining multiple types of noises at training time and observe similar increased robustness in the machine translation scenario. Training on and for adversarial noise is an important extension of earlier work on creating robustness in neural networks by incorporating noise to the network's representations, data, or gradients. Training with noise can provide a form of regularization and ensure the model is exposed to samples outside the training distribution. So, they've just in this part they've mentioned how you can incorporate adversarial examples at the training time and to make it more robust to different kinds of adversarial examples, because if you train it against only one adversarial setting, it might be that some other adversarial example where suppose there are some different perturbations in the initial example can lead to failure, so you ensemble them. Alright, so machine translation systems. The rise of end-to-end models in neural machine translation has led to recent interest in understanding how these models operate. Several studies investigated the ability of such models to learn linguistic properties at morphological, syntactic, and semantic levels. The use of character or other subword units emerged as an important component in these models. Our work complements previous studies by presenting such NMT systems with noisy examples and exploring methods for increasing their robustness. We experiment with three different NMT systems with access to character information at different levels. First, we use the fully character level models of Lee et al. This is a sequence to sequence model with attention that is trained on character to characters, so car to car. It has a complex encoder with convolutional, highway, and recurrent layers and a standard recurrent decoder. See Lee et al. 2017 for architecture details. The model was shown to have excellent performance on German to English, Czech to English language pairs. We use the pre-trained German or Czech to English models. Second, we use Nemetis, a popular NMT toolkit that was used in top performing contributions in shared machine translation tasks in WMT and IWSLT. It is another sequence to sequence model with several architecture modifications, especially operating on subword units using byte pair encoding. We experimented with both their single best and ensemble byte pair encoding models, but saw no significant difference in their performance under noise. So we report results with their single best WMT models for German or Czech to English. Finally, we train an attention sequence to sequence model with a word representation based on character convolutional network CAR CNN. The model retains the notion of word but learns a character dependent representation of words. It was shown to perform well on morphological rich languages thanks to its ability to learn morphologically informative representations. The CAR CNN model has two long short-term memory layers in the encoder and decoder. A CNN over characters in each word replaces the word embedding on the encoder side. For simplicity, the decoder is word-based. We use 1000 filters with a width of 6 characters. The character embedding size is set to 25. The convolutions are followed by tanh and max pooling over the length of the word. We train CAR CNN with the implementation in KIM 2016. All other settings are kept to default value. So they've just described the three models which they're going to use. These two models are pre-existing state-of-the-art techniques, and this is the model which they are adapting from previous work. The implementation of CAR CNN is taken from KIM 2016, and they are modifying it to use for their task. Alright, so for the data, we use a TED Talks parallel corpus prepared for IWSLT 2016 for testing all of the NMT systems as well as for training the CAR CNN model. They've summarized the statistics, so you will find the number of sentences, the number of words, the errors, the average number of edits per word in natural noise datasets, and the corresponding tokens of the token recall of those edits on training and test splits. This is the number of edit per word, and these are the token recall of those edits on test and training split. Alright, noise, natural and artificial. We insert noise into the source side of the parallel empty data by utilizing naturally occurring errors and generating synthetic ones. In order to facilitate future work on noise in NMT, we release code and data for generating the noise used in our experiments. Alright. So for natural noise, since we do not have access to a parallel corpus with natural noise, we instead harvest naturally occurring errors from available corpora of edits to build a lookup table of possible lexical replacements. In this work, we restrict ourselves to single word replacements, but several of the corpora below also provide access to phrase replacements. So for French, Max and Wisniewski 2010 collected a Wikipedia edit histories to form the Wikipedia correction and phrase corpus, Vicopaco. They found the bulk of edits were due to incorrect diacritics, choosing the wrong homophone, and incorrect grammatical conjugation. German. Our German data combines two projects, RWSC Wikipedia Revision Dataset and the Merlin Corpus of Language Learners. These corpora were created to measure spelling difficulty and test models of contextual fitness. Unfortunately, the datasets are quite small, so we have combined them here. For Czech, our Czech errors come from manually annotated essays written by non-native speakers. Here, the authors found an incredibly diverse set of errors and therefore phenomena of interest. Capitalization, incorrectly replacing voiced and voiceless consonants, missing palatalization, error in valence, pronominal reference, inflection, colloquial forms, and so forth. Their analysis gave us best insight into how difficult it would be to synthetically generate truly natural errors. We found similarly rich errors in German. We insert these errors into the source side of the parallel data by replacing each word in the corpus with an error if one exists in our dataset. When there is no more than one possible replacement to choose, we sample uniformly. Words for which there is no error are kept as is. Table 2 shows the number of words for which we were able to collect errors in each language and the average number of errors per word. Despite the small size of the German and Czech datasets, we are able to replace up to half of the words in the corpus with errors. Due to small size of the German and Czech datasets, these percentages decrease for longer words. So if there are more than 4 characters, then it's 25 and 32% respectively. Right. So they've just mentioned how they're getting noise. So for French, they're using this Wikipedia edit history. For German, they're combining these two corpus. For Czech, they're using these manually annotated essays. And this is the table they were referring to. Alright. So synthetic noise. In addition to randomly naturally collected sources of error, we also experiment with 4 types of synthetic noise: swap, middle random, fully random, and keyboard typo. Alright. So what is swap? The simplest source of noise is swapping 2 letters. This is common when typing quickly and is easily implemented. We perform one swap per word but do not alter the first or last letter. For this reason, the noise is only applied to words of length greater than or equal to 4. For following the claims of the previously discussed meme, we randomize the order of letters in the word except for the first and last because the meme claimed so. Again, by necessity, this means we do not alter words shorter than 4 characters. For fully random, this is because if you were altering, say, a 3-character word, then you wouldn't be altering anything because the first and last remain the same and the middle word then has nowhere else to go. For a fully random, we are unaware of any strong results on the importance of the first and last letters. So we also include completely randomized words. This is particularly extreme case, but we include it for completeness. For keyboard typo, finally using the traditional keyboard for our languages, we randomly replace one letter in each word with an adjacent key. So D is just beside S. This type of error should be much easier than the random setting, as most of the words is left intact, but does introduce a completely new character which will often break the template the system has learned to rely on. Alright, so failures to translate noisy texts. Table 3 shows blue scores of models trained on clean vanilla text and text on clean and noisy text. All models suffer a significant drop in blue when evaluating on noisy text. This is true for both natural and synthetic noise. The more noise, the worse the translation quality, with random scrambling producing the lowest blue score. The degradation in translation quality is especially severe in light of humans' ability to understand noisy text. To illustrate this, consider the noisy text in Table 4. Humans are good at understanding such scrambled text in a variety of language. We also verified this by obtaining translation from a German native speaker unfamiliar with the meme. As shown in the table, the speaker has no trouble understanding and translating the sentence. In contrast, the state-of-the-art systems fail on this text. So basically, you have this input, a human translated it, but the other models totally mess up. Our natural question is if robust spell checkers trained on human errors are sufficient to address this performance gap. To test this, we ran texts with and without natural errors through Google Translate. We then used Google spell checker to correct the documents. We simply accepted a first suggestion for every detected mistake and reported results in table 5. We found that in French and German there was often only a single predicted correction, and this corresponds to roughly +5 or more in blue. In Czech, however, there are often a large list of possible conjugation and changes, likely indicating that a rich grammatical model would be necessary to predict the correction. It is also important to note the substantial drops from vanilla text even with spell check. This suggests that natural noise cannot be easily addressed by existing tools. So if you have a look at this, the if you have the vanilla text, but even if you use the spelling typos correction from Google, still the performance is pathetic compared to the normal non-noisy outputs. So dealing with noise, structure invariant representations. The three NMT models are all sensitive to word structure. The char to char and char CNN models both have convolutional layers on character subsequences designed to capture character engrams. The model in Nemesis is based on subword units obtained with byte pair encoding. It thus relies on character order within and across subword units. All these models are therefore sensitive to type of noises generated by character scrambling. Can we improve model robustness by adding invariances to these kind of noise? Perhaps. The simplest such model is to take the average character embedding as a word representation. This means this model refers to as mean char. First generates a word representation by averaging character embeddings and then proceeds with a word level encoder similar to char CNN. The mean char model is by definition insensitive to scrambling because you're averaging it out, although it is still sensitive to other kinds of noise like key and nat. Table 6 first row shows the results of mean char models trained on vanilla text and tested on noisy. The results on vanilla text are by definition equal to those on scrambled texts. Overall, the average character embedding proves to be pretty good representation for translating scrambled text, while performance drops by by about 7 blue points below char CNN in vanilla, French and German. It is much better than char CNN's performance on scrambled text. So if you have a look here, if you have the vanilla network, if you have the vanilla score with natural noise, if you only use the mean char model, let me just check. Yeah, if you only use the mean char model, you can see the score against natural noise is better. If you only have the natural noise, if you also check for keyboard typos, it falls. But if you check for scrambled, I guess scrambled is pretty good because as they mentioned, the word embeddings, since they're using character level embeddings, and for each character, by definition in the mean char model, it takes the average of all the character representation or the character embeddings. Then it does not matter if the strings have been scrambled or not. Alright. So for black box adversarial training, to increase model robustness, we follow a black box adversarial training scenario where the model is presented with adversarial examples that are generated without direct access to the model. We replace the original training set with a noisy training set where noise is introduced according to the description in section 4.2. The noisy training set has exactly the same number of sentences and words as the training set. We have one fixed noisy training set for each noise type. As shown in table 6, training on noisy text can lead to improved performance. The mean char model trained on which are keyboard typos, perform well on keyboard typos in French but not in other languages. The model trained on natural noise perform well in French and German but not in Czech. Training the mean char model on noisy text does not appear to consistently increase its robustness to different kind of noise. The mean char model, however, was not expected to perform well on non-scrambling type of noises. Next, we test whether the more complicated Cas-CNN model is more robust to different kind of noise by training on noisy text. So the results are there in table 7. In general, Cas-CNN models that are trained on a specific kind of noise perform well on the same kind of noise. All models also maintain a fairly good quality on vanilla texts. The robust training is sensitive to the kind of noise. Among the scrambling methods, more noise helps in training. Models trained on random noise can still swap mid noise, but not vice versa. The three broad class of noise, scrambling, key, and natural, are not mutually beneficial. Models trained on one do not seem to help the others. In particular, only models trained on natural noise can reasonably translate natural noise at test time. We find these results indicate an important difference between computational models and human performance, since humans can decipher random letter ordering without explicit training of this form. Next, we test whether we can increase training robustness by exposing the model to multiple types of noise during training. Our motivation is to see if models can perform well on more than one uh, kind of noise. We therefore mix up three kinds of noise by sampling a noisy method uniformly at random from each sentence. We then train a model on the mixed noisy training set and test it on both vanilla and noisy versions of the text sentence. We find that models trained on mixed noise are slightly worse than models trained on unmixed noise. However, the models trained on mixed noise are robust to specific type of noise that they are trained on. In particular, the model trained on a mix of random keyboard and natural noise is robust to all noise kinds. Even though it was not the best on any kind of noise, it achieves the best result on average. The model is also able to translate this sentence reasonably. So if we have a look at the scores on different raw conditions, so on average you can see the model which was trained on all three kinds of noises on average outperformed the others, even though it might not be the best on every task. Alright, so analysis, learning multiple kind of noise in CAR-CNN. The CAR-CNN model was able to perform well on all kind of noise by training on a mix of noise types. In particular, it performed well on scramble character, even though its convolution should be sensitive to the character order, as opposed to mean car, which is by definition invariant to character order. How then can CAR-CNN learn to be robust to multiple kind of noise at the same time? We speculate that different convolutional filters learn to be robust to different kind of noise. A convolutional filter can in principle capture a mean or some operation by employing equal or close to equal weights. To test this, we analyze the weights learned by Cas-CNN trained under the four conditions. Three models trained each on completely scrambled words, keyboard typos, and natural noise. For each model, we compute the variance across the filter with 6 characters for each one of the 1000 filters and for each one out of 25 character embedding dimensions. Intuitively, the variance captures how much a particular filter learns a uniform versus non-uniform combination of character. Then we average the variance across the 1000 filters. This yields 25 averaged variances, one for each character embedding dimension. Low average variance means that the different filters tend to learn similar behaviors, while high average variance means they learn different patterns. Figure 2 shows a box plot of these averages for our three language models and four training conditions. Clearly, the variances of the weights learned by the random model are much smaller than those in other settings. This makes sense as with word scrambling there are no patterns to detect, so filters resort to close to uniform weights. In contrast, the key and natural settings introduce a large set of new patterns for CNN to try and learn, leading to high variances. Finally, the ensemble model trained on mixed noise appears to be in the middle as it tries to capture both the uniform relationships of random and the more diverse pattern of natural or key. Moreover, the variance of variances, the size of box is smallest in the random setting, larger in the mixed, and largest in key and natural. This indicates that filters for different character embedding dimensions are more different from one another in key and nat methods models. In contrast, in the randomized model, the variances of variances is close to zero, indicating that in all character embedding dimensions, the learned weights are of small variance. They do similar things, that is, the model learned to reproduce a representation similar to mean car model. The ensemble model again seems to find a balance between randomized and key nat. Right. So for keyboard, the variance is larger as compared to say random. Even in natural, the variance is larger. The ensemble is somewhere in between. So they've also pointed out that in the case of only randomization, the model tends to learn a small variance, so it is learning somewhat similar to what a mean care model is. Alright, so for richness of natural noise appears to be very different from synthetic noise. None of the models that were trained only on synthetic noise were able to perform well on natural noise. We manually analyzed a small sample of natural noise from the German dataset. We found that the most common source of noise are phonetic or phonological phenomena in the language and character omissions. The rest are incorrect morphological conjugations of words, key swaps, character insertion, orthographic variants, and other errors. The most common type of natural noise, phonological and omissions, are not directly captured by a synthetic noise generation and demonstrate that good synthetic errors will likely require more explicit phonemic and linguistic knowledge. This discrepancy helps explain why the models trained on synthetic noise were not particularly successful in translating natural noise. In conclusion, in this work we have shown that character-based NMT models are extremely brittle and tend to break when presented with both natural and synthetic kind of noise. We investigated methods for increasing their robustness by using a structure invariant word representation and by ensemble training on adversarial examples of different kinds. We found that a character-based CNN can learn to address multiple types of errors that are seen in training. However, we observed rich characteristics of natural human errors that cannot be easily captured by existing models. Future work might investigate using phonetic and syntactic structure to generate more realistic synthetic noise. We believe that more work is necessary in order to immune NMT models against natural noise. As corpora with natural noise are limited, another approach to future work is to design better NMT architectures that would be more robust to noise without seeing it in the training data. New psychology results on how human copes with natural noise might point to possible solutions to this problem. And then they have the acknowledgements. So overall, this paper was pretty interesting because they've looked at 4 different types of noises, and what really intrigued me was how a simple technique such as mean car is able to outperform everything, not outperform everything, but is able to perform better than the other models on random scrambling, just because it is invariant to the random scrambling, since it averages the word embeddings. So that was pretty interesting to see. Also, another pretty interesting result was the fact that even on after training on so much synthetic noise, the natural noise was not really being replicated, since the richness of natural noise uh, was not being acquired in the training set. So overall, I do plan to implement some of this stuff, but it was a great read. Thank you guys for tuning in. Hope to see you again next time.